Good day. I hope everyone is doing well during these troubled times. My name is Jay, the co-founder and CEO of Nears Lab. We are a South Korean company specialized in blade inspection using autonomous drone systems. And for today, I'm going to talk about when to start blade repair using drone-driven data to monitor defect growth. To analyze blade repair data, we first need to find out the root cause of certain defects. I want to categorize any defects generated with unexpected events as type A. These include incidents of bird strikes, hailing damages, and lightning damages. Whereas type B defects are naturally occurring defects. These include blade surface erosion, vortex generator loss, lamination damages, etc. And these defects indicate the deterioration of the blade over time. Within type A, accidentally caused defects, a turbine can generate either a severe or light damages, which can grow into severe damage if left undealt with. While type B defects are grown over time and also have the potential to grow into becoming a category 4 or 5 severe damages. Looking on this chart of annual O&M cost breakdown per turbine, we can easily see that part repair costs are a lot higher than the cost contributing to the farm's O&M budget. And when looking and comparing parts replacement costs over the entire turbine life, the 16 to 20 years turbine's consumable cost is significantly higher than the 0 to 5 year turbines. While the turbine deteriorates over time, the cost of part repair each year jumps severely. Thus, to prevent and predict the growth of defect would be a crucial part in preventing high O&M costs on repair. Then, what would be our ultimate task? Our task is to make the growth predictable from damage initiation to defect propagation. However, to build such model, there are a lot of challenges involved. A universal guide to predicting accurate and precise defect growth is not plausible through inspection. Each farm and each turbine are deteriorating within different environments and settings. As every human being is different from one another, each farm has its own unique characteristics and thus requires different treatment. The variables that affect the speed of turbine deterioration or defect growth include geographical, environmental identities, weather, and these characteristics contribute greatly to both generating a defect and the growth of the defect. The turbine's life cycle fatigue is highly related to the humidity of the area, amount of the precipitation, temperature, wind, etc. Apart from exterior impacts, the different material and structure of turbine also vary, which arise the challenge to build a universal model of defect growth. Other than physical variables, human factors should also be considered. Every farm has its own convention in damage categorization, the cycle of inspection, and repair schedule. All of these factors are critical to build a farm-specific case in order to monitor turbine status and to generate a unique predictive model that can prevent severe damages. After knowing why farm-by-farm cases need to be built, the data consistency and data management through inspection are the next challenges. To draw accurate comparisons through visual inspection over the years, the data generated needs to be highly precise and consistent. The management of the accumulated data also needs to be appropriately stored, organized, and accessible. With all of these challenges considered, predictive analysis model can be built on farms through accumulated visual inspections. This will lead to a clear understanding of a perfect time window to repair a defect and also help with budgeting the O&M cost of a farm. At the moment, Drone-based visual inspection are predominantly used in the industry to efficiently check the current status of the wind turbine blades. However, the inspection data driven from the drone inspection is not utilized to its maximum capacity yet to contribute to predictive analysis. For example, this is a typical type A accident-related defect upon drone inspection. What we have done with these image data until now really is analyzing the size and type of defects, delivering the facts to asset owners and operators, who then makes the repair decision based on their O&M budget. This is the same for type B defects. With increasing multi-year inspection data availability, defect can be compared to the previous year to analyze growth. This is an example of lightning protection system damage propagation over a year when we revisited the same farm. The white painting of the LPS has been peeled off compared to the first year. Again, another example of a defect growth comparison on a leading edge erosion. If you compare the 2 years of the blade, the erosion has grown with more lamination exposure. However, the severity of the damage hasn't grown significantly over the years. With the accumulated inspection data over a few years, defect growth predictions can be driven from the growth pattern of each crack. By using predictive analysis, farm owners can decide and allocate their O&M budget by comparing the defect's growth pattern. For example, farm owners and operators can choose to budget Category 2 defects with faster growth rather than budgeting a Category 3 defect that has not much. Or they can also look into all Category 3 defects to budget the ones that have higher potential to grow into Category 4 or 5 in the following years. Here, at this point, I would like to coin a term, repairman cycle. Repairman cycle describes the damage initiation to its repair. With the information on the first cycle, we can then continue monitoring the status of the blades and build a second replacement cycle. So, how should data be captured, processed, delivered, and managed to build predictive analysis model? Until now, this is a typical drone inspection to result delivery flow. We use drone to capture inspection data, make it visible on an online platform, then produce AI tag inspection reports. This is no doubt the most efficient, precise, and economical option for inspection. Now, we would like to take another step and found a norm on innovative inspection. I'd like to propose the following stages toward predictive farm management by getting the most out of the drone inspection data. Stage 1 and 2 remains the same as the current workflow. Stage 3 involves building an annual farm snapshot and dashboard view after yearly inspection. By using the yearly farm snapshot, we move into stage 4 of doing the multi-year inspection to draw comparative analysis. With that, stage 5 will be repair management to track defect history and defect cycle to complete the farm management cycle. Each stage is crucial in predictive farm management. Stage 1 will be using AI-powered autonomous drones to capture inspection data. This ensures the quality of the data is precise and uniform. At NIRSLab, we provide inspection services and we also offer lease option for our platform. After the collection of data, stage 2 involves managing and delivering inspection results. Throughout our Zoomable online platform, clients can go through and view high-quality inspection photos, and they can also filter specific cracks and pull online reports or PDF reports out of the platform for repairment and archiving. With stage 1 and 2 being the foundation, we can then create an overview of the farm. It puts together all of the defect data for operational managers to see the condition of the farm in a snapshot. This annual overview will be produced every year after the farm's yearly inspection. By gathering data from multiple years of inspection, we are finally able to draw comparative analysis to monitor defect growth. The visual comparison gives viewers a good idea of how exactly the crack has become. Quantitative analysis helps us to understand the number and types of defects propagating to the next severity category. And lastly, managing repair would be the last stage toward building a predictive farm model. Asset owners can manage repair tasks, track repair history, make notes on the downtime caused by the repair, and they can also draw cost analysis on cracks to find the most economical point to start the repair. Having repair history managed on the same platform, a defect lifespan from initiation to development will all be stored in one place. When a defect has completed the first full defect cycle, it gives the second cycle a good reference point. Overall, using drone-driven data, we can build a defect prediction model through the 5 different stages of monitoring and management of the defects. This not only allows farm owners to plan ahead and know when exactly to start blade repair, but also help them to create smart budgeting strategies to save cost. So, when to start blade repair for your farm? Start using drone-driven data to build a farm-specific data model to find the predictive repair cycle today. Well, that's all for me today. Thank you very much for listening. Please feel free to reach out to us if you have any questions or if you have any other ideas on how we can improve the industry's management system together as a whole. We'd love to hear your thoughts. Thank you.